Hello everybody, welcome back to our channel. In this episode we're going to be solving a fluid transport practice problem. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe. It really helps a lot. So feel free to pause the video in order to copy the instructions. The problem that we're going to be solving is your instructor decides the easiest way to deal with stress is to invent a system that pumps refreshing beverages up to the roof of their house, 4 meters above the pump, where the beverages can be quietly enjoyed in the warm sun. The density of the soda is the same as the water. So points 1 and 2 are both open to the atmosphere. The beverage flows out at a rate of 6 times 10 to the negative 4 meters cubed per second. The area at points 1 and 3 is 10 centimeters squared, and the area at point 2 is 0.8 centimeters squared. There is no resistance in this system. So the first thing that we have to do is find the speed of the fluid at points 1 and 2. So as you can see, I have everything written down here in my notes. So this is the system. This height difference is 4 meters. Points 1 and 2 are open to the atmosphere. The density of soda is equal to the density of water. And we have the flow going out of the system over here. And then we have these areas. And basically what we have to find is what are the velocities at point 1 over here and the velocity at point 2 over here. So let's just go ahead and get started. So I think that the easiest way to do this would actually be, since we have the flow rate over here and we have both of the areas, I think that the easiest way by far to solve part A of this problem is to use our definition of current. So by definition, current is equal to area times velocity. And we do have the flow rate going out of 2. But we know, because we talked about continuity in lecture, that whatever comes out of here also has to be going in here. So even though they gave us what seems to be just the flow going out, they also gave us, you know, the flow over here and the flow over here and the flow at each point over here, because this is a closed pipe. So this is equal also to flow at this point. So now it's just a matter of crunching out numbers. So if I use this definition, B1 is equal to the flow at point 1 divided by area 1. So the flow is 6 times 10 to the negative 4 meters cubed seconds. And the area at point 1 is equal to 10, but this is centimeters squared, so we do need to work this out. So this is just going to be, you know, 1 centimeter squared. We have 1 is 100 centimeters, 1 meter is 100 centimeters, and then we have to do this twice to eliminate the centimeters squared. So if we want to change this to meters squared, we do need to divide by 10,000. So this is, well, there's just 1 times 10 to the negative 4 meters. There we go. And then this is 0.8 times 10 to the negative 4 meters squared over here. So area 1 times 10 to the negative 4. Okay, I'm sorry, I made a little mistake. I copied 1 times 10 to the negative 4, and I had 1 times 10 to the negative 4 over here because I forgot that this was a 10. So this is a 10, and then the conversion is times 10 to the negative 4. So this should have been a 10. This is a 10. And then this is 6 divided by 10 because this cancel out. So this is 0.6 meters per second. So now for B2, this is just, you know, the same flow divided by area 2. So this is 6 times 10 to the negative 4 meters cubed per second. And this area is 0.8 centimeters, so this is 0.8 times 10 to the negative 4 meters squared. So this is this cancel out, so this is just 6 divided by 0.8 So this is equal to 7.5 meters per second. And this is it. This is the final answer for part A. We got both of the velocities by just using a little bit of continuity, because we know that this flow has to be equal to this flow, and by just using the definition of flow rate. So let's just see. Part B is how much energy density does the pump add? So we do have a pump over here in between points 1 and 3, and basically they are asking us what is E pump divided by volume, because they are asking us for the energy density that it adds. So at this point, I think that it's pretty obvious that we have to use our Bernoulli equation. It is the only equation that we have in which this term shows up. Another thing is that we need to use Bernoulli from points 1 to 2 or 1 to 3. That would also work, I guess. Because if we don't cross the pump, then we are going to cancel this term, and that's not going to be useful because this is what we want to get. So what I'm going to do is, just by looking at the information that was given, I was given these two pressures. So I'm going to go ahead and do Bernoulli from points 1 to 2. Because if these two are equal, then delta P is equal to 0. And if I go, so this is 1 to 2. If I choose to go from 1 to 3, then delta P, I have absolutely no idea what that is. So I'm going to have two things that I don't know on the same equation. So that's not going to work out. So yeah, I'm going to do Bernoulli from points 1 to 2, knowing that delta P is going to be 0. So let's just go ahead and do that. So Bernoulli equation is just the full thing. Minus IR. This is equal to 0 because I'm going from 1 to 2, so it's atmospheric pressure on both sides. This is not going to be equal to 0 because I do have a height difference, so this term is going to stay. This thing over here, oh no, this is not equal to 0. The velocity is changing, and actually I already have my velocities, so that's going to be very convenient over here. This is what we're trying to figure out, so of course it's going to stay. It's also between points 1 and 2, so we do have to keep it. And resistance is equal to 0 in this problem, so this does go away. Okay, so this is it. I just need to put some numbers on the calculator. So let's just see. Rho, I'm going to use 8,000. Gravity, I'm just going to go with 10. This delta Y is equal to positive 4 because I'm going up 4 meters. This is 1/2. Rho again, going to use 1,000. This is final minus initial, so this is 2 minus 1, 7.5 squared minus 0.6 squared. So let's just go ahead and get that number. So this is 1,000 times 10 times 4 meters plus 1/2 times 8,000. 7.5 squared minus 0.6 squared. There we go. So I'm just gonna copy my numbers, 67945, and this is, you know, joules, meters cube, or pascals, or whatever you wanna. Both of them are the exact same thing, but this is the final answer over here. I don't know if the solutions use 9.8, so just be mindful about that. I'm rounding numbers over here, but just so long as your procedure is exactly the same, then you know you might get a slightly different answer, but that doesn't really matter. So now point C is asking what is the gauge pressure at point 3. You do not need to show any work for this question. Okay, so this is actually easy, and they are right. You actually don't need to work this out again. So first of all, the gauge pressure is your absolute pressure minus atmospheric pressure. then these 2 points are at atmospheric pressure, which means that if I use Bernoulli from 1 to 3, then the delta P that I would be finding is 3 minus 1 final minus initial, so this is 3 minus atmospheric pressure. So if I use my Bernoulli equation, I would get P3 minus atmospheric pressure. So basically, if I calculate my Bernoulli equation, what I'm gonna get is my gauge pressure. Just look at this. Just look at this. So if I use my Bernoulli equation from 1 to 3, essentially what I would be calculating is the answer to this question, because this is atmospheric pressure. And furthermore, if I use my Bernoulli equation from here to here, there is no change in height. So let's just there is no change in height, so this term goes away. There is no change in area, so this term goes away. There is no resistance, so that doesn't even show up. And the only thing that I have is this term over here. So this is E pump divided by volume, which I already calculated in this part over here. So my answer is essentially same number, same final answer. There we go. And this was calculated by just remembering the definition of what gauge pressure is, and just realizing, hey, if this is atmospheric pressure and this is the definition, then if you use Bernoulli, essentially what you will be getting as an answer is the gauge pressure that they were asking you to get. And that's it. So I really hope that you find this useful. If you do, please leave a like, or if you have any questions, feel free to leave a comment, and I will be reading those pretty soon. So I'll see you guys in the next video.